Briefly, Dr. Jahmour Givans is visiting us today, tomorrow, and a bit of Wednesday. So in particular, modeling systematics for current and upcoming surveys and telescopes. And he's also interested talking to us about modeling Lyman-alpha for it and the Lyman-alpha. Folks online, feel free to use the chat. I'll be monitoring it, so I'll make sure your question gets to Jahmour. And before you start asking. Okay, thanks everyone, and please take it away.
All right. Invitation, Martine, and for being a great host so far. I trust that will continue over the next couple of days as well. Thanks everyone else for the great conversation and the chance to be here, visiting our neighbors up north when the weather is actually better than I thought it would have been. So like Martine said, today I'll be talking about modeling the Lyman-alpha forest and the Lyman-alpha cross halo power spectrum. I chose to talk about this in part because apparently it was a fan favorite to the committee and they asked about it, so I like to deliver when I can. Secondarily, I could talk about some of the CMBLSS stuff I do, but it would basically be 90% background and then 5 slides of here are my errors that I'm getting in the code. And that's not going to make a great time for anyone. So instead, I'll just talk about something that was completed and as well. And I'm sure that he can answer some questions as well and can save my back if needed. So if you want to know, but you're also welcome to talk to me. Last time I checked on the schedule, I had pretty wide availability tomorrow. So by all means, let's begin. We're doing the game of cosmology. So I know CITA, the Canadian Institute for Theoretical Astrophysics, so I probably don't need to explain much of it to most people, but not everyone's a cosmologist. So just to get us up to speed, ultimately we're trying to play a game where we really want to study the origin and evolution of the universe, particularly on the largest scales. You know, what's large versus what's not large is not necessarily a debate I want to jump into, but we're thinking roughly galaxy scales and clusters of galaxy scales and beyond that. And scale structure, and to get a better hold on what the universe is doing, understand some physics along the way. Used to mean that is baryonic acoustic oscillations. Each of the points I've highlighted in red, I'll go into a little bit more detail in the coming slides. So you're welcome to ask me about those at those slides. BAOs for short, they're particularly useful if you're trying to find out something about, say, the Hubble parameter. So the parameter that describes the general expansion history of the universe from as early as we can tell until today. Similarly, you can use BAO to measure the angular diameter distance. So have a sense of how distances in the universe have changed over time. And collectively make a standard ruler. At slightly smaller scales, you can also incorporate redshift space distortions, which are really our probes for growth of structure in the universe. And distinct from those, but similar-ish, you can also use Alcock-Paczynski effect, sort of the AP test, if you want to get a sense for what the Hubble parameter is outside of just making some of these direct measurements. Within cosmology, we can also play the game with the Lyman-alpha forest and other probes where we want to test general relativity, and I'll talk briefly about how one could do that. And for those who have more particle physics bent, there's also the opportunity, especially if you're looking at the Lyman-alpha autocorrelation, of trying to constrain beyond standard model physics. So if you want to understand something that the standard model doesn't explain, such as neutrino masses, to constrain different models of dark matter, warm, ultralight, axion, dark matter, those kinds of things. We can do all these things in cosmology. And if you don't restrict yourself to just Lyman-alpha forest, you can do a lot more, but I won't go into those topics. I'll just stop here and discuss acoustic oscillations. Again, not quite synonymous with large scale structure, but oftentimes when someone says LSS probe, they think BAO. So it's worth understanding that a little bit. So in the universe prior to recombination, so before redshift 1100-ish, it existed mostly as a soup, if you will, dominated by photons and baryons in this plasma. And you can imagine little dark matter clumps being seeded throughout. And what that meant is that we had this tug of war effect going on where the gravity attracted all the fluid in toward the dark matter. And then fluid pressure naturally wants to expand outward. So you have this kind of inside and outside motions, compressions and rarefactions. And that generated these standing sound waves in this plasma. And these sound waves would become important, especially as the universe expanded and cooled a bit. That's somewhat described here. So in these 4 panels, we're starting at pre-recombination universe, just before recombination universe, but about when it's happening. And then I jumped ahead a bit to, say dark matter of your baryons in blue, your photons in red, and neutrinos in green. These all, and the photons and the baryons are really clumped together in this plasma. Neutrinos were already somewhat free streaming at this point. They free streamed about a second after the Big Bang, but even at this stage, they look not too far off. So everything was clumped together, and then the photons and the baryons got kind of pushed around together and stayed more or less in phase. Neutrinos, of course, continued to do their own thing. And the dark matter distribution started to broaden a little bit in terms of scale. And if you jump ahead much later, you notice that there's the original peak where the dark matter clump is. The parsecs. So when you see this, or when observers see this signature in the correlation function, what they know is that this particular scale corresponds to the method for understanding what distances are to different objects you're looking at and how far away standard ruler. And again, that's a pretty large. So you can look along this direction I labeled green here with delta theta. It's transverse to the line of sight if your telescope's down there at the bottom. And then you're looking along the wave that's coming to you. And you get a measure of RD. Well, RD you might know from the CMB. Delta theta you can measure, and the redshift you know in principle. So you can get angular diameter distance. Or along the line of sight, you know RD, you know the redshift, and you can get the Hubble parameter. And for as opposed to real space, what does that mean? It means that anything transverse to your line of sight's pretty much unaffected, but things along the line of sight end up seeming displaced from their actual position because you pick up a contribution from your velocities. So along the line of sight, if you think you're at x equals 11 in some arbitrary units, then maybe you're actually at x equals 10, and then the velocity is just pointing you this way. Or maybe you're at x equals 12 and the velocity is pulling you this way. So we make these actual measurements in redshift space instead of real space. And with redshift space distortions, you can constrain quantities such as the growth of structure, where you take, and particularly usually constrain this thing f sigma 8, where if you think of sigma 8 as like the clunkiness of the universe, and f is the logarithmic growth rate of the universe, you combine those two things and say, I can measure this at different redshifts because I can measure the BAO or the redshift space distortions at different redshifts. And then I kind of know how the evolution of structure has grown over time. And another distortions, but it's a similar effect. And in so many words, what it means is that you could imagine if you were to recreate the 2D baryon acoustic oscillation feature in the clustering of galaxies, it should be spherical because the universe doesn't have a preferred direction. And if you put in some, cosmological parameters, in particular a Hubble parameter that's wrong, and you try to get out the actual shape of this thing, is going to come back to something that's not spherical. Depending on redshift space, if you get Hubble parameter wrong, you're going to get this shape wrong. And you'll know how to calibrate your system well based on looking at that. Yeah. There are a ton of ways to do this, and you have this entire zoo of modified gravity models, and we could spend multiple people's careers trying to figure out how one can use cosmology to constrain gravity. But the arguably simplest one would probably be to just compare the growth of structure that you measure from redshift space distortions or otherwise to the predictions from general relativity. General relativity, it so happens, has a nice functional form that says, if you give me the Hubble parameter, I tell you what growth of structure is. So you look for that in this guy and you compare the two. And if they match up to within your error bars, then you say, okay, GR looks right. It has more support. If it doesn't match up, well, there might be a problem. And oftentimes people that deal with modified gravity or, for that matter, also, right, modified gravity and dark energy, for those of you who've studied the Weinberg ideology, an idea. So you might be able to ask yourself, am I getting standard cosmological constant dark energy where the equation states minus? So something strange like that could also happen, and we could test for that. Here I more or less emphasize just a couple of different points. So one of those is, what are the neutrino masses? So here we have all the neutrinos on a scale where these are, M1, M2, M3, where we don't actually know what they weigh, and we would like to get a sense of what that is. We know from theory, we get something like, I think it's 0.06 EVs, or like 60 MeVs as like the actual lowest baseline one can get from the standard hierarchy of neutrino masses, but it gets something like 100 MeV from the inverted hierarchy. So which of those is true? We don't know. Inverted hierarchy is effectively increasing masses, but then it's a third neutrino, much lower mass than these. Normal ordering, because 1, 2, 3. And then if it's a lower mass, it's the inverted hierarchy where 3, 1, 2. And you can test different models of dark matter. You can have standard cold dark matter that makes building blocks of the universe, or you can make warm dark matter that tries to destroy structure and doesn't allow you to have all the wonderful things we say today. And in principle, dark matter is so unknown, and it can be so many things that, instead of it all being cold or all being like slightly warm, it can be, 90% cold and 10% warm, or a little bit hot. There's about those, but these are just some of the little things we like to try to understand. We get why the Lyman-alpha force is useful. But before doing that, I should first say what it actually is. For, in this case, just say redshift, like we'll say 3 quasars littering throughout the universe, isotropically distributed, and they all shoot rays of energy along our line of sight. So if that photon emits at a certain wavelength, and that wavelength gets redshifted down to exactly 1,216 angstroms, and that happens at a location of a neutral hydrogen gas cloud, the hydrogen atoms in that gas cloud can absorb that photon. So what you end up seeing is something like this little cartoon here, simply where, okay, it emits with some high flux, and then we shifted lines, and you know the absorption is always at 1216 angstroms, you can put that information together to say, I have a gas cloud at redshift, whatever. And then we could do that along multiple sight lines and then get a sense of where the neutral hydrogen is in the universe. And then, you know, tracing back and doing the math, okay, there was, if this quasar is at z equals 3.62, maybe they're there. Okay, but you know, that seems a little bit hard, and it is hard. And you might ask yourself, well, we have galaxies. You know, galaxies I can kind of like pinpoint on the sky. Why do I want to do any of this? Sound keeps dropping out. Yes.
Can you give a line of sight between you and the thing in front of you?
Okay.
Possibly you're turning away.
Oh, okay.
Oh,
But we do have galaxies. So you might want to ask yourself, why the Lyman-alpha forest? This particular slice of time, and also this particular slice of scales, galaxies are working out here, depending on, you can get really big scales, but you're mostly at early times. The primary CMB, of course, very early times, very large scales. Weak lensing will get you down to like fairly small scales, but late times. So the Lyman-alpha forest cuts out a nice little wedge here, or I guess a box really in this redshift space versus scale distribution. Objects out here is just not quite as dense. And then you have the Lyman-alpha forest and those types of quasars out here closer to redshifts of, you know, 3-ish. So it allows you to explore a large volume of the universe as well. Quasars in the Lyman-alpha forest, without mentioning the arguably the most important experiments to come and use some of that information, at least in terms of Lyman-alpha forest. So one of those, and it contained a bunch of Lyman-alpha forest spectra from over 160,000 quasars, mostly located between redshifts about 2.2 and 3. And that covered 10,000 square degrees. And the immediate follow-up to BOSS was eBOSS, just extended BOSS. And by the time that was done, we had gotten about 500,000 quasars over 6,000 square degrees between redshift of 0.8 and 3.5. What's shown here is, I couldn't find an the red dots or the red circles. It shows eBOSS, the LRGs, which are a particular type of galaxy sample plus the quasars. So, you know, at a large fraction of the sky with that. But now, you know, for the longest, we were talking about DESI as something that's kind of in the future. (14,000 square degrees. And by now this number is even a little bit outdated. I think it's something like within its first several months, if not even first year, we had already gotten 400,000 quasars above redshift 2.1. So those are the quasars we would typically call our Lyman-alpha forest quasars. And it represents an order of magnitude improvement in volume and I guess I'm not formally a member of DESI anymore, so I can't really talk too much about the details of it. But or you know, early. All right. the surveys, but what is the actual project here? So most cosmological science results that we're using in terms of Lyman-alpha forest come from correlation functions. So you're just measuring, you're correlating the position of one thing and the position of something else. And there are three types of correlations that are relevant in this case. One is the autocorrelation of the Lyman-alpha forest. So if you have these blue circles here that represent quasars, and then the dashed lines pointing toward Earth are like the spectra of those quasars, then you take the position along one quasar sight line and the other, you correlate that over different separations. There's the autocorrelation of quasars, which is kind of like galaxy autocorrelations, position of quasar 1 and position of quasar 2 correlated. And then there's the cross, where you take the position of quasar 1 and the spectrum from quasar 2, positions along that and correlate. And what this project wants to do is it wants to use simulations to measure certain power spectra. And we're going to use some old models, old meaning they already existed in the literature prior to us working on this project. We're going to make some new models independently of that. And we're going to compare both of those to simulations and test how well the old models can do, see how well the new models can do. And in order to do that, we're using this set of simulations called the Sherwood simulation. I guess a handful of years ago. And it contains 17.2 billion particles in volumes that range from 1,000 to 160 cubed, h to the minus 3 megaparsecs cubed. And in terms of the box size and the resolution, it makes it really ideal for IGM studies, in particular for the Lyman-alpha forest. And by certain metrics, these metrics in particular, it's probably considered the best simulations to date. It uses this kind of smooth particle hydrodynamics, so these SPH codes, one of those being P-Gadget3, which is just like a certain updated version of Gadget 2 that people might be more familiar with. And they're run with a Planck cosmology in a box that's 160 megaparsecs on the side. And we're taking for most of our analyses, we're taking a single snapshot at redshift 2.8. So the actual Sherwood simulation outputs that I have are at redshift 2, 2.4, 2.8, and 3.2, which pretty well traces Lyman-alpha ranges. But they're pretty expensive to run, and we were best able to get the results at 1 redshift, so we went with 2.8. The video here that's now done is kind of showing you one cutout from, I think, an L equals 80 megaparsec box, where you can see the density field and how that connects with the H1 fraction, and compare that to the temperature and the vacuum. Yes.
So, can you just comment a bit about, what's done for like ionizing sources in these images?
Yes. I would, off the top of my head, I honestly do not remember. I know the exact resource to point you to, and I should remember it, but unfortunately, I do not. I think they were treated. Yes. I don't think there was any particularly brand new tricks that were done that haven't been done.
Is it like a uniform ionizing background? Or?
I think it is uniform ionizing background. Yes. I remember, I don't think there was a patchy reionization or anything like that put in. I think it was fairly uniform. Yes. Alpha forest and halos, yes. But in practice, things, surveys like DESI and BOSS before it, they were particularly looking at quasars. And instead of playing the game where we say, okay, well, how does a quasar populate a halo and exactly which halo should have all the quasars at this particular redshift, we were a little bit looser and just kind of assumed our highest mass bin of halos are the locations of quasars. So one can, of course, take exception with that, and it's completely understandable to do so. But as a kind of proof of concept, we're going to pretend that at redshift 2.8, about 14, those are where we're going to say the quasars exist. So our box again is just 160 megaparsecs, and we have these really high mass objects. And as you can tell just by looking at the numbers, that 10 to the 5 halos of sufficient mass. So we kind of had to make some cuts in order to just get some reasonable results. And what you can tell by here is in the dashed lines we plotted noise becomes 10% out here at k equals 0.3-ish. That noise, and then later on I'm going to talk about more limitations and things we would like to be able to do better. Result, but it is nice to know we actually got some good power spectra out of these boxes, where the 4 panels are dimensionless. Flux power spectrum, so the auto power spectrum of flux, the auto power spectrum of halos, their cross power spectrum, and then this thing, which is basically measuring the correlation coefficient between the two, which is saying, and then I divide that by the geometric mean of the 2 auto spectra, how well the I think probably the bottom 2 panels are the most informative. Because the spectrum should be, just of a single sign. Cross correlation we expect to be negative because the Lyman-alpha 4 trace, Lyman-alpha 4 tells you where matter is by showing you where matter is not. Because where there is flux, nothing absorbed it, so there's no matter. Where there's not flux, something absorbed it, so there is matter. So that's why you get the minus sign. But we plotted that, and it's counted here. Is that we did this approximation that's very common in Lyman-alpha simulations called the quick Lyman-alpha approximation. Close to your quasar, or where the quasar would be, or very high mass density regions in general, you just artificially remove the gas within, like, say a virial radius or so of that halo. And reasonable amount of time. But the net result of that is now, instead of flux being anti-correlated with matter position, flux close to the halo gets correlated with it, because now you see flux because there is no matter near this high density thing, but a high density thing has matter. So it's a little weird. Interesting is a point I'll come back to in a bit, which is that you notice you can't really just use nine, then you're fine out to like right. But we did not plot any error bars for this. So, take that for what you will. So if you look up the literature arguments from some of the BOSS papers, it'll tell you like what kind of variance per mode you expect for the auto spectrum of the Lyman-alpha, for the halo auto spectrum, and for their cross spectrum. And you get something in each case that's proportional to the power spectrum of the thing. Same term where you have ineffective is basically the number density of sight lines within some region you're looking at. And P1D is the 1D power spectrum. And for the cross power spectrum, it's sort of this combination of both of these guys in an interesting way. fitting procedure, we were able to ignore these terms. The argument missing wasn't too bad, so we could throw that away, mostly because we could get a tight enough density of sight lines. We have a box, we can do whatever we want in simulations. I don't think I wrote it here, but there was a general noise floor term. We also included in the Lyman-alpha auto spectrum and all the rest of them. And that's because the high K modes were starting to dominate our fit. And it was basically a way of downweighting those modes ever so slightly, so that way the large scale features could be more important. Yes. I was talking about the correlation a few slides ago where the sight line from quasar 1 and the sight line from quasar 2. P, the power spectrum, is you take the Fourier transform of that correlation function. And in practice, I would say that most observers and people that work with the data and present the results often do that in correlation function space. And most theory tends to be done in power spectrum space. Yes. Pretty much your standard process. You minimize a chi-squared. In our case, it's not really a real chi-squared because we have that noise floor issue. So I'll use later because, again, we can't really trust them too well. But we did use them as a general, comparison between the two and say, okay, this fake chi-squared is a little lower than this one, so it probably helps out. We brought down our noise a little bit because we do have a box. So we said, let's measure the power spectrum along all 3 axes. So instead of just like line of sight Z and you take force measurements like that, that's, one realization. Let's do it again along X and do it along Y. So then out of one box for free, you got like 3 times the sample. Modeling portion of this. So the modeling is interesting because the very simplest modeling has now been around for many years. So the work of Kaiser, Nick Kaiser, 1987, in theory, but I think it's safe to say that any ubiquitous model that you see in perturbation theory probably traces back at least a little bit to this one, where Kaiser was talking about it in the context of galaxies. So again, where it says the power spectrum of the tracer you're looking at, in our case, the Lyman-alpha forest, is equal to something, which I'll explain, times the matter power spectrum, L for linear, the large scale power spectrum. Where this and mu is the cosine of the angle between whatever K you're looking at in the line of sight. So the power should change according to the line of sight that you're looking at. And that's the well, and it just has 2 unknown parameters. And again, if you want to do large scale physics like the BAO, that's basically all you need. But one of the purposes of trying to study large scale structures also to study into the quasi-linear regime or so. You want to have a little bit more corrections than that and do something better. So sense and run it through the best simulations that were available in 2003. The final McDonald model is just this times this. And there's some parameter you fit for alpha P, alpha V, KV. And we would have some amount of physical motivation for what these are, but we're just going to do it and see how well they work. I mean, that. by Andreu Arino-Prats, said, let's kind of, so let's see if, the McDonald model still holds up, or if I can make this simpler in any kind of way. So you already have two that are free from here. And here you have one for most purposes, so you get down to like 5. And there's also hidden here a couple others. So like I think McDonald was actually like 8, and this one ended up being pull this out of thin air. But if you want to think about it, this accounts for nonlinear growth power spectrum. So the matter power spectrum times k cubed over 2 pi squared, just to make. So that accounts for nonlinear growth of structure. There is a here just kind of acts isotropically. And then you have the particular line of sight. All right, so how well do those models perform? Well, Arino's model, the 2015 one, the somewhat newer one, is the dotted lines. And then the McDonald model, the slightly older one, is the dashed lines. And there is another plot down here with the residuals. New bins. So red meaning most along the line of sight. Dark blue meaning least along the line of sight, so most transverse to you. And so that was a result. We had where we said, okay,
has the flexibility of the model that has enough.
have the freedom, minimize the number of free parameters you need while trying to recover the actual measurements as best as you can. Both of them could do that pretty equally well. And we're going to make the statement that we prefer Arino because you have 3 fewer free parameters. You're still at 5, which is a lot to marginalize over. I won't sugarcoat that, but you have less to deal with.
But if you want
So some of those have a more strong physical significance, and for that, I think if you know the physical significance of a certain parameter and you trust your simulations to do a good job, at least at that, I think you can more or less fix them. You would, in principle, want to fit them to data and leave a certain amount free. But I think in practice, when people have done this in the past, like Arino and McDonald have been applied to real data before. I think in practice, when they've done that, people have mostly gotten some of these, harder to physically interpret parameters from the simulations, tested their cosmology, bit little results, and said, okay, we're going to fix these and just solve for some other different parameters of the model.
And so then when you then look at different simulations that have different like gas parameters, and different
Yes,
feedback parameters,
yes.
those models that work as well describing different.
Or it's been this one particular snapshot. There's, I said this was like an SPH code by the Nottingham group, and they're Sherwood simulations. But there are also some slightly different simulations, like the NIX NYX simulations that people, I think, have tried to apply, not necessarily these models, but maybe some older models too, as well. For so many different simulations in general is expensive. We've been limited in our cases of, this one set of cosmology and this one simulation snapshot. And I definitely think next is to try this with more or less independent simulations that make slightly different physical assumptions about the universe and seeing how robust it is. And again, there's also the argument to be made that, well, now we're getting a lot of good and real data. So you can apply it to the real data, but then you have to marginalize all the parameters that you don't understand well. And what's the trade-off between I can make a more confident model. Yeah. Yes, Martine.
I guess how complicated is it to make these Lyman-alpha mocks from any given set of spin? So a game to
Tell, listening to the conversations in DESI, it has been, for the postdocs that have been working on it, mostly, it has been at least a, more than a year-long effort to go from, and partially it's going to depend on how much experience you have with these and how well they're understood. But in particular, for something that's like DESI level accuracy, where you really want to get all your physics right and do everything, perform all your proper, I guess, null tests and anything else, you have to, it's a lot of work to do. Also just computational resources as well. NERSC has an amazing allotment of resources, but they have to be shared, not just among the Lyman-alpha group, among the Galaxy people as well, everything else. Yeah. Maybe I can just ask Jim Simons to let me run them for like ever on the infinite CCA resources. But I will also save that for, yes, sorry. Yes, I would say as a problem that's going to be DESI's is that in the real data, you're really going to have an issue with quasar redshift errors. So the redshifts and the actual location and space of the quasars are fairly well understood, but you're using certain lines in the quasar spectra to say this is at z equals, I don't know, 2.1. But you use a slightly different line, a slightly different technique. You're at, this might be z equals 2.3. And that might be small for some purposes, but it might not be that small for other purposes. So if your delta z is a little bit larger, then I think somewhere along the lines I have cutoffs for like when your redshift errors, the expected redshift errors for DESI are going to suppress the power by like 50%. And then that'll actually impact the scales we care about. So it'll be skipping ahead slightly, but you're going to find that like somewhere around like here, we can just draw a cutoff line. Like, I don't know, that's like, I don't care if I can get the Lyman-alpha power spectrum that well here, like anything to the right of this, because for this mass bin, the quasar redshift error, sorry, for this mu bin, the quasar redshift errors are going to be, so they're going to be half of the signal, and I don't care anymore. But want to model them. So quasar redshift errors are definitely what I'm thinking of is probably the biggest thing. Yeah. I think at least part of it's intrinsic. Yeah. It's I think the Quasar errors can be improved like by a certain amount, and I think they have been improved a little bit between, or they will be between the jump from EBOS to DESI. Out of memory, I don't know, like, you know, a 10% improvement or a 50% improvement. I think there's a small improvement, but I still think that's probably going to plague us for a minute. All right, so from 3 dimensions to 1 dimension. So we have a 3-dimensional model, and I just showed you the results of that. But it's also true that the smallest scale constraints, when people are publishing a lot of these Lyman-alpha papers, do come from the 1D power spectrum. The flux line here correlate for all the different lines. 1D is kind of interesting because it's like along the single skewer, basically correlation 10 voxels back with 30 voxels back or something. It's pretty much the 1D power spectrum measurement. And you can get that by just taking the 3D, integrating it along the transverse direction and solving. So then we looked at, all right, we had a 3D model that we know works, the Arrhenius model in particular. What prediction does it make for the 1D power spectrum, and how well does that perform? And we plotted those residuals, where blue is just a different axes. Remember, I said we took this along 3 different sight lines. So red's the average of the blue lines. Base. Here you can attribute that to like cosmic variance. Your box is only a certain size. We need bigger boxes. That's one of the take home. Anything. Well, this entire like middle trough is done surprisingly well as far as simulation. Opens up to building emulators for 1D power spectrum from 3D sims instead of having to run brand new sims for 1D by it. Okay, modeling the halo power. Be in the big mass things, so you have shot noise problems. You can use one loop perturbation theory. You can throw on the fingers of God effect, which distortions. If I look at all the halos and I don't care about the mass bin, then this dot dash line is the shot noise that we're hitting. So shot noise kicks in pretty quick. So that already tells us we can't do super well. I'll everything people have done was mostly a Kaiser model, that linear theory. It only looks a little different here than it did several slides ago, because now we have the bias terms from the flux and the bias terms from the halo. They had to be separated out instead of having like AB squared and something in parentheses squared. We split it into 2 pieces that it came from. So then let's see, Cassie-Lacus and others in that paper. So they modeled the reasonably small scale Lyman-alpha cross halo spectrum with a Lorentzian. That's like, I guess, 0.6, 2 pi over R, roughly. Too hot on. And then in one of the, I believe it was an EBOS paper, Remember McDonald, I told you a while ago, we have linear theory and we tack on like some multiplicative correction to like do it better. They said we have linear theory, we have some finger of God turn, and we multiply that by it. We in it, and the portion that does not have any wiggles. Did good again, but they didn't. Excellent work, definitely told us a lot of good science, but can we do better in terms of smaller r or larger k? The best models that I told you we know is going to fail eventually because of this. And this is all with data, right? So even if I have a model that fits this 100% perfectly, and both of those 100% perfectly, the cross model is not going to fit 100% perfectly because we have this fall off. So we know it's going to fail automatically, but it's a starting point. And the problem with doing this, other than just knowing it's going to mess up, is that if I'm saying we want to use the best fit models, we have a theory problem, which is that the square root of the flux power spectrum, because that's proportional to delta, but is delta, because you have like delta plus delta squared, delta cubed, and all that, and you square root that, and it's not proportional to delta. So it doesn't make too much conceptual sense to do that. It's a little bit safer to just use linear theory for the halo power spectrum instead. Is I never actually tried to fit any parameters to the cross model. From the forest, which gives me all of this bit, pose that on top of my, if I just take that as it is, and I throw that and I compare that to what kinds of fits we get to the actual data in the largest mass bins, then the one you get is labeled here baseline. So this dotted line, okay, for red. Fine, worked a little bit, not quite. So then we played the game of, all right, ad hoc, just see what we can do and make things fit, if we can make things fit. And one term that we came across after enough effort was, let's take this next, that's going to vary with the highest mass halos versus the lowest mass halos, where parameters. This again is a dimensionless power spectrum, so we know it. K is just K and mu is just mu. And I multiply that a thing I don't actually mention here directly, but it ends up being true, is that basically 0. So you can throw away this whole correction piece and just take it's quite nice, all things considered. It's the dot dash line, and it really halos, also because we're approaching the edge of the box, but no features too much. And luckily they didn't, basically. If you and then the extended fit, so that last model I showed you with different colors depending on your mu, Only real differences pop up like down here, right? In corrections, the scales are supposed to be much smaller than the BAO. Actual quasars with a box that's 160 megaparsecs. But if you just get a bit much bigger box, then maybe you lose resolution because you have to run it a lot longer to get. Models don't know implicitly about limits on the correlation function. So and you saw here, like our models. The one on the left shows a comparison of two different sizes, and for different simulation resolutions. Again, not quite the convergence we would hope for, but it's kind of the best we could do right now. Transverse direction and the line of sight direction, which seem to show better convergence compared to the box size and resolution. But one could, again, take fault with that and yet be justified. And I will conclude with a few comments, is that this is as far spectrum measurements that have been done. We confirm the accuracy of the Lyman-alpha. And we showed that you can use the latter to simultaneously predict the 3D and 1D power spectra of the Lyman-alpha forest. It's the first model, or sorry, we presented the first model to get the residuals of the cross power spectrum within 10% out decay of about 1. And we demonstrated that you don't really change the BAO much, which is nice. There's room for improvement for reasons I mentioned too before. And going forward, the best way to test this, we think at least, will be on actual data, which the DESI members are welcome and encouraged to do. And hopefully I'll get a message from someone saying, hey, the model was helpful. So I think that's all. Thanks.
Okay, thank you so much.
Nice talk. So I noticed that it is 4 p.m. So if anyone has to run to meetings, around for maybe 5 more minutes, we could take a few more questions and then bring the conversation upstairs afterwards to the post.
So let's take now, if you can check it out. And otherwise, is there
In the room who would like to ask any further questions? Quite a lot. I'll start.
So Matt McQueen has a paper. He models the laminate forest as actual absorbers, and then he created kind of a table model formalism to model the power spectrum. So I'm actually wondering whether it's going to be useful for this kind of study, because I feel like the absorber model is more physically intuitive, and in simulations you can actually locate where the absorbers are. Especially you're working on redshift 2 or 3, the things really look like absorbers. Yeah, so I feel like maybe that's going to be better in terms of providing you with a physically intuitive picture than just trying to model the power spectrum and fitting a bunch of free parameters.
I agree with that. I think, probably the political answer, it's worth doing multiple approaches and seeing what works best. But I do agree when you can aim for some physical understanding, it's certainly much better. And, there's a large community of people who have done halo models in the case of halos and galaxies, of course. So I think there's a lot to be learned from that approach. I look forward to, seeing that and, tested against other simulations and tested against real data as well. I say that with us approaching this problem and trying to do this sort of modeling as opposed to something like a halo model, I think was mostly driven by the somewhat brief but still strong history that people within model and the Rignoud-Protz model. So we were trying to follow a similar vein in that and saying, okay, if these worked out well enough for you, then hopefully this new thing can work out well enough for you. But I certainly welcome any type of modeling that for what it's worth, while we didn't have a being a little less easy to understand, there was a general, pressure term. There was a general thermal broadening term, things like that. You could get in the halo model. Yes.
What extent can one assume that the gas in the Lyman-alpha forest is hydrostatic in gravitationally relaxed halos, as opposed to it's in a more dynamic state where, I guess, rather than internal energy release driving flows, maybe ionization energy sources driving flows, or there's, it's falling in or flowing out, or maybe not even the topology of a halo?
So I would say, I think we kind of was for the gas that's near the halos and the quasars themselves, you're going to have a lot of feedback. Certainly, I wouldn't imagine them being in any sort of really good equilibrium. But so much of the gas that we actually look through in the universe, like outside of the halos, are sitting out there in the IGM, where if you're sufficiently far enough away, I think the hydrostatic assumption works reasonably well. And I would say that's probably a mostly smallish scale feature. It's true that we should better model it, but if you're far enough away from the halos, I would think that you could probably get by with saying we're in some kind of equilibrium state.
I was just wondering,
Bigger simulations.
Mhm.
Do you need them for more statistics, or do you need them for better growth of the
Mhm.
like,
Yes.
So the bigger box, the simplest thing it does, it gives us more halos. But also in a bigger box, even halos aside, the Lyman-alpha forest on the larger scales where we are actually measuring it for BAO and stuff, you're not going to have that big cosmic variance that I showed you before, where at small K it was like flapping all over the place.
this correctly, that what you were mainly looking at was like small scale effects anyway, or like.
So for that study, it's still important to get the large halos because we're assuming that's where the quasars are. So the cross correlation between the two on small scales needs to be done well. Yes.
All right. Okay, so let's thank our speaker again.